Okay, I'm going to go ahead and do 13.4 to illustrate how this works. Um, so first off, they gave us a beam with loading condition. That is 6 meters long. 6 kilonewtons there. There is no support, so it's overhanging. There's a roller. And then there's a hinge. And then there's a distributed load here of 3 kilonewtons per meter across 2 meters, 2 meters, 2 meters. Okay. So what's my first step? I need to find reactions on the beam. And my overall goal, I want to know the internal shear at points A, B, and C, and D. So A, B, C, D. Okay. So step one, find reactions. So I'm going to break this down into a force diagram, free body diagram. And this is a rolling joint at B. I'm going to assume it's positive for now. This is some sort of, I'm going to call it By. And so I've got this distributed load. I'm going to assume it's a point load. And since it's a rectangle, it's going to be base times height. The base is what? 4 meters across. Height is 3 kilonewton per meter high. So when you multiply those out, 3 kilonewton meter, 4 meters across, you're going to get 12 kilonewtons. 12 kilonewtons. And its centroid is halfway with a rectangle. So that's going to be 2. So 12 kilonewtons. And now I've got support at point D, which is, let's say dy. And it's a hinge joint here, so I'm going to have a dx. Cool. So first thing I'm tempted to do is sum of forces in the x. 0 dx is my only force in the x direction. So it's 0. Now I have 2 forces in the y, so if I did sum of forces in the y, I would have negative 6 kilonewton plus by minus 12 kilonewton plus dy, and that's 2 unknowns. So I would need another equation, which is sum of moments. And now I want to pick my sum of moments about my unknown point to make this easier. Or about, let's do B. And so this is 2 meters, 2 meters, 2 meters. So I've got 6 kilonewtons at 2 meters in a positive direction. 6 kilonewton, 2 meter, positive. And then I've got 12 kilonewtons at 2 meters in a negative direction. Negative, 2 meters, 12 kilonewtons. And then I've got 4 meters to dy in a positive direction. So 4 meter dy. So this is 24 kilonewton meters. This is 12 kilonewton meters. So this one was positive, negative, positive 4 dy. So, and they need to be 0. I forgot that. So now to solve for dy here, we're going to add 24 kilonewton meters to both sides and subtract 12 kilonewton meters from both sides. So I'll get 12 kilonewton meters plus 24 meters, and then that's 4 dy. Then I'll reduce that and then divide by 4. So I'll have 12 kilonewton meters divided by 4. So dy is 3. Oh shoot, that's a meter, kilonewtons. So my reaction in dy is 3. So I could plug that back in up in my sum of forces. So then I can solve for by by adding these two values and subtracting 3. So that's 18, 15. So then by is equal to 15. Okay. So I'm going to do my force diagram again. This time, I'm going to include my distributed load. Kilonewton. So B here was 15. And then I'm going to mark this as a distribution. And then this one was only 3. This distributed load was 3 kilonewton per meter. Okay. So now when I consider shear within the beam, this is point C, D, B, A. So I'm going to cut first to find my shear force at A. So A is maybe like an infinitesimal section here with a load of 6 kilonewtons. And now I must have a counter to that in the cut itself. And there's no distance yet, so there is no moment. So at point A, you've got a shear, and I'm going to write shear as V. Yes, that's what they're doing. And it's going to be they have negative. Hang on. So this is their positive convention for shear. And so it's saying if you take a cut, so your beam is traveling and you cut it down is positive. Whereas if you came from the other direction and you cut it up is positive. So it's going to be really important to keep that consistent. Same with when you cut the beam and check for moment. Okay. So because I cut and my beam's on the left, up is negative in this case. So for me, it would make more sense to cut from the right then. So that up would be positive. So in that case, let's do D. So D, 3 kilonewton. So you've cut it. Basically, there's no thickness. There's no distance to travel at all. And so the beam is reacting with 3 kilonewtons. And so the shear at D is -3 kilonewtons. So traveling along, I want to make a cut at C here. So now things actually get interesting because there's distance involved. So I've got a 3 kilonewton reaction. And then I had a loading like this that was 3 kilonewtons per meter. And this is 2 meters. So again, I'm just going to simplify that down into a point load to find this reaction at this cut. 3 kilonewton. So that's 3 times 2, which is 6 kilonewtons. And it's halfway across, which is 1 meter. So 1 meter here. So my reaction here needs to be 3 kilonewtons. So sum of forces in the y, 3 plus 3 minus 6. You also want to check if there's a moment to keep it from spinning. I don't think there is. This is probably a 0 moment spot. No, there's. Oh yeah. But if you wanted to check, it would be sum of moments, and then pick a point. So like right here. C 0. So then you've got 6 kilonewtons 1 meter away. Negative direction plus 3 kilonewtons 2 meters away. So you just get nothing. Oh, and then in this equation you would include your reaction moment here. So you'd have like a moment inside of the cut. Oh gosh, why am I doing this to myself? Ran out of space. And then you would solve for that like moment reaction. And it, in this case, ended up being 0. So I've got a V at C equal to 3, positive. Now I need one more, and that is at B. So I've got a distributed load across the entire cut here. Because I cut at B. B had this roller. There's a reaction here, 3. And then B was 15. Like that. C is somewhere in the middle there. 2 and 2. Okay, so I want to find that reaction again at the cut that will satisfy, also including this 15. So this is interesting. So there's going to be within the beam, there's going to be a discontinuity in the shear, depending on whether you go to the right or the left. So you're going to want both answers here. Let's include this. What was this? 12. 2. So you're going to say shear in B in the positive and shear in the B in the negative. So to the left and to the right. So that you got two static problems here because you have just a point load on your area of consideration. So I've got this. And there's just the reaction in this scenario here. If there's no point load yet, so that would be to the right. And I hope that's the positive shear one. So in this scenario, the amount of force we need is what, 9 kilonewtons, positive. And then in the next scenario, 3 kilonewton, 12 kilonewton, and including 15. Now the beam itself, just after that, will have to react against that 15, right? I guess not. Sum of forces are 0, so this is also 0. So after you suddenly include that 15, it's 0. And I think in the next problem they go into how to plot that. So I'm going to go ahead and start doing that. Let me break this. Okay, this is going to be example 13.5, which is to plot the same problem that we just did, and hopefully it makes more sense with the plot. Get this in focus. So yeah, it's the same loading conditions, same reactions, and then they're going to do the shear diagram. I'm going to focus on the shear diagram for now. Okay. So I'm going to gather up all my data points I just got from example previous to this. So I've got shear in A, and I think that was negative 6 kilonewtons. Shear B, I just got that one. 9. Shear C, 3, positive 3. Shear D, negative 15? No. Where did I put it? Oh, negative 3. Okay. So with that on the side there, I'm going to draw my beam loading. So 6 from the top. I've got a reaction, 2 away of 15. I've got a distributed load all the way to the end from B of 3 kilonewton per meter. These are 2 meters to C, 2 meters to D. 4 total. D has a reaction 3. Okay, so that's my free body diagram. So now I want to draw a shear diagram. And I'm going to start it, let's say, this is my beginning of the beam. So this is like position 0. So to the left of A, there is no beam. So the shear is 0. This could be my 0 then. And right away, I have a negative 6 shear downwards. So I don't know if I want to draw it to scale or not. I'll just do it right here. So that point is -6. So at A, it goes from 0 abruptly up to 6. And now inside of the beam, there's nothing really happening. So it's just going to remain 6. Okay, until there's an abrupt change from the reaction. So I'm going to travel over to B, 2 meters. Now there's an abrupt plus 15. So I'm down here at -6, and I add 15, so I'll end up at 9. So let's add another square here. So very sudden change because that's how these point loads act. Now I have a distributed load. And so the distributed load is constantly adding shear force into the beam. So for every meter that you travel, you get 3 kilonewtons down. So if this is 1 meter, I'm going to subtract 3 from 9, which would be here. So this is 9 positive. Subtract. So this is going to be 6. So here I have 3. I should have hit 0, so my scale's a little wonky. Dang it. How far off am I? Just 1. Good. This is my actual. Okay. So I still have a distributed load. I've only gone 3. So there's another meter to go. So I end up at -3 here, kilonewtons. And now I have a disjointed 3 to take me back to 0. And then this is my. So there's like whoop. So let's draw in my 0 point. Okay. So that's sort of how I think of a shear diagram. We did just go through and characterize what shear should be at each one of these points. So VA -6, VB 9. Let's see, boop. VC should be 3. This was C here, halfway between. And VD is -3. Okay, and then after the beam's over, it's 0 again. Yeah. Now I think we need to go into the relationship between shear and bending.